Hi there, welcome to the Senior Physics video on light and waves. In this video we're going to look at apparent depth. Now, have you ever wondered that when you look into a fish pond and you look at the fish swimming around, or you look at the stones at the bottom of the pond, they always seem to be a lot closer to you than they really are. And if you went to try and grab a fish, you'd actually miss it. Firstly, because the fish would swim away, and secondly, your perception of where the fish actually is to where the fish really is, there is a difference. Now, what we're going to do in this video is try and explain why that difference occurs and how can we calculate either the actual depth of the object or the virtual image depth based on the media that we happen to be working with. Well, firstly, let's deal with question one and see what is the reason, or how does an image get to be closer to us, especially when we're looking at things in water. Okay, so here we have an example. We've got a water layer, which is shown by our blue line, and that's going to be separating off our two media, air at the top, water at the bottom. We've got a person who's going to be looking at a fish. Now, the fish obviously is our object, and the person obviously is the eye. Now, from the object, in order to see the fish, what we've actually got is reflected rays from the sun, which is going to be hitting the fish and bouncing into that person's eyes. So we'll take a couple of reflected rays from the same point of the fish. So here's a reflected ray, which I'm going to then refract against the normal into air. Now, obviously, remember it's moving into air, so the refracted ray is going to be greater. I take another beam going from exactly the same point. Now, this is going to be at a different angle of incidence to the normal, as you can see there. So I'm going to get a different angle of refraction. Now, at this point, where the eye is, the beams do not converge. They do not cross, so we don't get a real image. So what we actually have to do is track back from each of the refracted rays. So I track back with the first one, I track back with the second one, and you can see the 2 points cross. Now, the point where they cross is where our virtual image is going to be formed. And as you can see, our virtual image is a lot higher than the actual objects. What actually happens is our brain doesn't take into account that it's going undergoing refraction as it moves from one media to the next. All it does is take the light beams that are coming off and track them back to a point where they converge, and that's where our image in our brain is centered. So it's a virtual image, and it pulls the object up. Now, the question is then, how much is it pulled up? Well, with everything that we've looked at so far, it's all down to the density of the medium. Okay, obviously the denser the denser it is, the more refraction we're going to get. So we have a calculation which will allow us to calculate the depth of either the actual object or the apparent object. Now, the equation we use is n equals true depth divided by apparent depth. Now, n is the refractive index of the media that we happen to be moving from, and the true depth obviously is the depth of the object. The apparent depth is where our brain places the image once it's captured all the light. So let's use an example. So here's an example. I've got to find the apparent depth in water, which has a refractive index of 1.3, and the true depth of the object is 2 meters. So it could be a coin sitting at the bottom of the pool 2 meters away. So I use the formula n equals true depth over apparent depth, and basically I'm going to rearrange it so that I can then find what the apparent depth is. So I'm going to swap over apparent depth and refractive index. So I get true depth divided by the refractive index will give me the apparent depth of the image, which is 2 divided by 1.33. So my image is going to be 1.5 meters from the surface. So basically it's half a meter higher than where the object obviously is. Now, if you go on and in this post on the course, if you go on, I've done another example video for you of how we can work through a more complex answer, but it's fairly straightforward. So n equals true depth over apparent depth will give us the calculation, and then we need to understand that as the beams are refracted away, our brain tracks back to a point where they converge, and that's where our image is, and that's why it's always higher. Okay, well, I hope that makes sense, and join me again. Thank you for watching.